In this podcast, we'll be going over techniques used to solve simple motion problems. Now, when solving any motion problem, we have a few tools at our disposal. We have our definition of position, our definition of displacement, which is change in position, our definition of average velocity, which is change in position over time, our second definition of average velocity. Remember, this is only good when an object is accelerating at a constant rate, which is the final velocity plus the initial velocity divided by 2, which is just like your grade point average, and our definition of acceleration, which is change in velocity over time. We also can use some algebra and create new equations out of these, which are really the same equation, just written a different way. So we have that for an object that's going at a constant velocity, or when you're using the average velocity, we have the change in position equals the velocity, the average velocity times time. For the same object, we have the change in time equals the displacement divided by the average velocity. And for an object that's accelerating, we have that the final velocity equals the initial velocity plus the acceleration times time. And these really just come from, these two here just come from this equation. And this one down here at the bottom comes from our definition of acceleration, just written a little bit differently. So most simple motion problems that we have can be solved by using one of these equations. You can read the problem, figure out what you know, figure out what you're looking for, and find one of these tools, which are really models of our motion. So use one of these models to solve whatever you're looking for. And usually there's going to be just one variable missing, and you can plug in your numbers and get an answer out fairly easily with a little bit of knowledge of algebra. Now, there are a few types of more complicated problems that we're going to deal with where you can't just use one of these equations, where you have to use multiple equations, or sometimes you call simultaneous equations, where you have to use one equation to get a new piece of information and then use that new piece of information in another equation to keep getting new pieces of information until you get enough where you can find out what you're looking for. So one type of these is when you're trying to find the average velocity of some object when it's done different types of motion, and you want to find an overall average velocity. So in this case, we have Sarah here going to her friend Mike's house. So Sarah takes a 200-mile trip from her house to her friend Mike's house. She travels the first 100 miles going 50 miles per hour. She hits traffic and slows down to 40 miles per hour for the next 30 minutes. Sarah stops and takes a 45-minute break for lunch, and then finishes the trip going 80 miles per hour. What was her average velocity over the entire trip? Now, there's a lot of stuff going on here. There's a lot of numbers. A lot of numbers that are kind of the same type of numbers. So in cases like this, it's definitely worthwhile to either draw a table or do something to help organize your thoughts and organize your numbers while we try to basically translate this problem from a word problem into a physics problem. So what I'm going to do is, because there's 4 different pieces to our trip, there is the first 100 miles, the next half hour, the 45-minute break, and then the end of the trip. I'm going to draw a table that cuts up her trip into 4 different sections. So in each section, we have section 1, section 2, section 3, and section 4. For each section, I have a displacement, I have a time, and I have a velocity over that section. These are really average velocities, but only over that section. Also on the top of my table, I put her total displacement, which in this case is the same as her total distance traveled, the total time for her trip, and her average velocity over her entire trip. Now, I can also use the fact that because there's 4 pieces to her trip, if I find the 4 pieces and I add them up, they're going to equal the total displacement for a trip and the total time for a trip. Now remember, I can't do that with the velocities because they don't work that way. So I'll just keep them separate for now. Now some of you might say, hey, if we just find the 4 velocities, we can add them up, divide by 4, just like we did with our grade point average, and get the total average velocity for the trip. But there's 2 problems with that. One problem is Sarah's motion is changing all the time. She's doing different types of motions. So that equation is really only good if you're constantly accelerating. In this case, she is not. She's doing different types of motions. The second reason is that each of her motions are weighted differently. It's like if you're in an honors class or an AP class and a standard class, in some schools, you have each class is weighted differently. The AP class is worth more than the standard level class. So in your grade point average, they don't just multiply the numbers and divide by, or add the numbers and divide by the number of grades. They actually weight the grades differently. And that's kind of what's happening here. So we can't just add up the velocities and divide by 4. That won't work in this case. But what we can do is we can use our definitions of an object that moves at a, or I'll use our model for an object that moves at a constant velocity, and the three different equations we have for that, to find as much as we can about this problem, and hopefully when we're done we'll have enough to get her average velocity for the entire trip. So let's start off by just writing down what stuff we know from the problem. So it says Sarah takes a 200-mile trip. Well, that's the total distance traveled for her entire trip. So I actually already know that the delta S for the entire trip is 200 miles. She travels the first 100 miles, so the first part of the trip is 100 miles long, going 50 miles per hour. So I know the velocity over the first part of the trip. She hits traffic and slows down to 40 miles per hour, so that's the velocity over the second piece of her trip for the next 30 minutes. So she's traveling the second part for 30 minutes. Now we got to be a little bit careful here. Because our velocities are written in distances per hour, miles per hour, we want to make sure we use all of our times in hours. In this case, we're given minutes, but we know that 30 minutes is 1/2 of an hour. So I'm going to write it down as 1/2 of an hour for her second part of her trip. Sarah stops and takes a 45-minute break. So again, we're given some time in minutes. I'm going to write that as hours. So 45 minutes, if you divide it by 60, you get that is 3/4 or 0.75 hours. Now it says she takes a break. Well, what's that mean? Well, break means that she's not driving. So you might say, oh, we can just leave that out then. She's not doing anything. Well, remember, no motion is a type of motion. In this case, it's nice because no motion is always easy to deal with. So her velocity when she takes a break is going to be 0. And she also doesn't go anywhere. So her distance traveled when she takes a break is also 0. And then she finishes the trip going 80 miles per hour. So over the last piece, her velocity is 80 miles per hour. So all the stuff here in yellow is what we know from the problem. Now the next question is going to be what can we find out using our equations? Well, over the first part of her trip, we know how far she traveled, 100 miles. We know her speed is 50 miles per hour. So we can actually find the time it takes for her to travel that using the fact that the time that it takes something to travel is the change in position over the average velocity, which is going to be, in this case, 100 divided by 50, which gives us 2 hours. So we got something new. That's nice. All right, over the second part of her trip, we know the time it took her over the second part, and we know her velocity. So if we want her distance traveled, that's just going to be her average velocity over the second part times the time it took her to travel the second part. So that's going to be 40 times 1/2 of an hour, which is just 20 miles. Now the third part of her trip we're all set with. We know everything about that. All that's left is the fourth part of her trip. And it looks like we don't know enough. It looks like all that we have is her velocity over the fourth part of her trip. We're missing the time she was traveling for, and we're missing the distance. But we were given one more piece of information. The problem told us that the total trip was 200 miles. So if the total was 200 miles, the first part was 100 miles, the second part was 20 miles, the third part was 0 miles. That means the fourth part had to have been, right, 80 miles long. So we do know enough to get the distance traveled over the last part of our trip. Now again, we can use the definition or use our model of constant velocity motion. With the fourth part of our trip, use this version of the equation. And we get the time it took her to travel is going to be the 80 miles divided by 80 miles per hour. Look at that, nice number. 80 divided by 80 is just going to be 1 hour. So now we know everything about the pieces of her trip. All that's left is to add them up and to get a final average velocity over the entire trip. So we're already set with the distance traveled for the trip, 200 miles. The time is going to be 2 hours plus 1/2 an hour plus 3/4 of an hour plus another hour. You do a little math. Hopefully you can do it in your head. You don't need a calculator. But you get about 4.25, or not about, but actually exactly 4.25 hours. Then if you want her average velocity for the entire trip, you're going to use the time for the entire trip and the displacement for the entire trip. So that's going to be 200 miles divided by the 4.25 hours, which gives you an average velocity over the entire trip. Again, it's always good when you're doing math before you typed in your calculator. Just do a quick guess to make sure you didn't type something wrong. Well, this is really close to 400 divided by, or 200 divided by 4, which would give me 50. The denominator is a little bit bigger, so I should get a little bit less than 50. And in this case, you get about 47 miles per hour for her average velocity over the entire trip. Now another type of problem that's a little bit tricky is something when an object is accelerating, speeding up or slowing down, and you want to figure out the distance that person traveled while they were accelerating, or the distance the object traveled while it was accelerating. So in this case, we have Jessica's driving 75 miles per hour. She's being a bad girl in a 45 mile per hour zone. She sees a cop and steps on the brakes. Her car slows down at a rate of 5 miles per hour per second. How long does it take for her to slow down to the speed limit, and how much distance does she need in order to not get caught by the cop? So in this case, we have Jessica driving a car. She slows down. There's a cop ahead of her. She wants to try to slow down to the speed limit before she gets to the cop. We want to figure out how much time she has and how much distance she needs to not get a ticket, basically. So in problems like this, it's always good to organize your thoughts again, try to translate the word problem into a physics problem. And I like picking out 3 different things. I like writing down what stuff I know from the problem, writing down the model that I'm going to use to solve the problem, or models I'm going to use to solve this problem. Remember, models are really our sets of equations that describe what's going on. And then the last step is just to solve the problem. So the knowns here. So it says Jessica is driving 75 miles per hour. Well, there is her initial velocity. That's what she's doing in the beginning. And she's in a 45 mile or a 40 mile per hour zone. So we know later on it says she wants to get down to the speed limit. So her final velocity is going to be 40 miles per hour. She slows down at a rate of 5 miles per hour per second. So her acceleration, again, if you can't exactly, it doesn't say acceleration there, but we can tell by it's saying this number is telling you how she's slowing down for one. And also look at the units. These are units of velocity units per time. The only thing that has velocity units per time is acceleration, but we got to be very careful. It says slows down, and the slows down just tells us we want to put it, in this case at least, we want to put a negative with our acceleration because we called the initial direction she was going positive, so this is going to be a negative acceleration. So we got negative 5 miles per hour per second. And actually with your knowns, I should have mentioned this before, I always like to write down what things I'm looking for. Even though I don't know them yet, they are the variables involved in my problem. So it says how long does it take? Well, how long does it take is asking you about a time. So I'm going to be looking for time. And how much distance. So now next we have to pick what model we want to use here. So in this case, Jessica is slowing down at a constant rate. So our model is going to be a constant acceleration rate. And we have a few equations that work with that. We have that her velocity equals her initial velocity plus her acceleration times time. We also know later on she wants to know how much distance traveled. So we have to use our model of average velocity because right now it's the only tool we have to find distance traveled. But we're missing one thing. Our acceleration model has final and initial velocities. Our distance travel model over here, our displacement model, has average velocity. So we need a way to get from initial and final velocities to average velocity. So we can use our second definition of average velocity for constant accelerated motion to help solve this problem. So let's start by getting her the time she needs to slow down. We can use our first model. So in our first model, we know her final velocity. We know what her initial velocity is. We know what the acceleration is. We're just looking for the time, so we should be able to solve it. So we know that 40 miles per hour equals 75 miles per hour plus negative 5 miles per hour per second times time. Solving this for time, we get negative 35 miles per hour equals negative 5 miles per hour per second times time. So the time it takes her to slow down is going to be 7 seconds. Now the second part is we got to figure out the average velocity that Jessica is traveling. Her average velocity is just going to be her final plus her initial, so 40 plus 75 over 2, which equals about 57.5 miles per hour. Now the last step is just going to be to use our answers in the first two parts here to solve her final answer. So we get her, the distance she travels to do this is going to be her average velocity, 7.5 miles per hour, times the time she was traveling for, is 7 seconds, which gives us an answer of about 403 miles. So some might say, hey, wait, whoa. That does not seem right. So this girl is slowing down for 7 seconds. She traveled 403 miles. What did we do wrong? Remember, it's always good when you're done with the problem to see if the numbers make sense. In this case, this seems ridiculous. It took her 403 miles to slow down. So let's look back and see if we can figure out what we did wrong here. Now it looks like our first two steps are perfectly fine. There's nothing wrong with those. But when you look at our third step, look at our units. We have miles per hour times seconds. Now we like the time pieces of each of these to cancel out. The hours should be canceled out by the time unit, and we're left just with miles. But in our case, they don't. We have miles per hour multiplied by seconds, and seconds don't cancel out hours. So we made a mistake with units here. So let's get rid of this. So that was not. So to turn seconds into hours, we can just divide this, or times it, basically times it by 1. But we're going to say that there are, in 1 hour, there's 3,600 seconds. So our time in seconds is actually only about 0.00194 hours. And now in our final step, when we find how far this girl traveled, we're going to use her same average velocity, 57.5 miles per hour. But we're going to multiply it by the time in hours, 0.00194 hours. And this gives us a distance traveled of about a little more than 1/10 of a mile, which makes a lot more sense. So as you can see, for most motion problems, or at least simple motion problems, you can just use a combination of the tools that we have. Some problems are very simple. You just plug in numbers, you get an answer. Some problems take multiple steps, but each step isn't very hard. The math is not what's to be afraid of here. Each step, the math is fairly straightforward. The hard part is going to be to figuring out which miles to use and what order to use to get everything that you're looking for.